Yeah, okay then. So, hi everyone, and welcome to another session of the Bangalore Theory Seminar. Today we have Madhumita Kundu as our speaker, who will give a talk on FPT approximation via random walks. Madhumita is a final year PhD candidate at the University of Bergen, Norway, where she is co-supervised by Saket Saurabh and Pekka Parveen. Prior to this, she received her bachelor's from Jadavpur University and master's in technology from IISc Kolkata. Her research interests span multiple areas within theoretical computer science, including parameterized complexity, graph algorithms, and FPT approximation. Over to you, Madhum.
Okay, thank you for the introduction. Okay, so today I'll be talking about FPT approximation via random walks. So this talk is based on the paper that is to be appeared in Stock this year, and this is co-authored with Ishan Chakrabarti, Tanmay Namdar, Ariel Kulik, and Saket Swaran. Okay. Yeah. So here is the outline of the talk. So I'll pick Vertex Cover as a running example throughout, like Vertex Cover, maybe different variants of Vertex Cover. And first I'll explain FPT algorithms and then some FPT approximations, then what it means by time ratio trade-off, and then introduction to our results, and then later on how to view like probabilistic branching as random walks and so on. Like we'll gradually build and then we'll see how much we can finish. Yeah, all right. So we start with the okay. So we start with the definition of vertex cover. Yeah. So it is a classic problem. So it's for everyone to be on the same page. So input is an undirected graph, and there is an integer k, which is the parameter. And the question is, does there exist a set of vertices of size at most k such that every edge has to be incident to those vertices? In other words, for every edge, at least one of its endpoint will be index. And such a set is called vertex cover, and it is really one of the old problem like which was shown to be FPT. And yeah, so today like mostly the definition is pretty easy to keep in head, and I'll explain everything in terms of like taking this as a running example. Okay, so yeah, okay. For example, here is a 6 vertex graph, and I want to find a solution of size at most k is equal to 3, and then see v1, v2, v5, and v3 is indeed a set of size 3, and you can see that every edge is incident to one of these vertex, or at least I mean both of them can be incident, but at least one of them. Okay. So now I'll start with APT algorithms for vertex cover, and then gradually go to things of our paper. Okay, so what is the simplest uh, uh, branching algorithm the vertex cover can have? Okay, so the simplest branching algorithm is that, okay, so first, I mean, you check the base cases, if there is no edge to be covered, then you say, or trivial, you say yes, and if k is less than 0, then you say no. Or otherwise, when you are not in the base case, then what you do, you pick an edge arbitrarily and branch on the two endpoints of it, which means what, if gk is an instance of vertex cover, then you branch in one branch, you branch on u, and basically the parameter drops by 1, and in the another branch you do the same thing for v. Okay, so now look at the search tree. What is the search tree? Basically, how this is a recursive algorithm, right? You start from G, and then you go to two residual instances, and then if at least one of them says yes, you say yes. Otherwise, you say no. So this is, if you look, like open up the whole branching tree, this looks like this. And here at every side, the solution reduces by the solution, or we can say measure, reduces by 1 in every side, and it is two-way branching. So so clearly its height is at most k, and number of leaves is at most 2 to the power of k, and which plays a role in the running time. Yeah. So it is pretty obvious why this is correct. Why? So let's see. Suppose V is a vertex cover of size at most k. I mean, for that matter, any vertex cover, and we know that let U be the age that algorithm picked. We know that at least one of them has to be in S, right? And let U be the vertex which is in S. So then you go to that branch, G minus U, K minus 1, that branch will be correct. And from there you extract the solution. From there you take the solution, add V to it, and that is your overall solution. Okay, so now what's the running time? Clearly, like the measure drops by 1 in every branch, and it is two-way branching, so it leads to 2 to the power of k type. 2 to the power of k type branching algorithm, and where order star hides the polynomial factor. Like at every node of the branching tree, how much time it has spent to do all this polynomial work, that I'm hiding. So the exponent is basically 2 to the power of k. Okay, so this is the most basic FPT algorithm for vertex cover. So now let's look at another branching algorithm which leads to a better base. Like instead of 2, it is better than some other number better than 2. Okay, so the first two base cases are pretty similar. So now another thing is that, okay, so now at the moment, instead of branching on a vertex, I will branch on branching on an edge. Instead of branching on an edge, I will branch on a vertex, but a vertex of degree at least 2. So what if you don't have a vertex of degree at least 2, which means the maximum degree of the graph is at most 1, and which means it's basically matching an isolated vertices which can be solved in polynomial time. So now we assume that there exists a vertex of degree at least 2, and then basically you branch as follows. Either V goes into the solution or all of its neighbors goes into the solution, right? So yeah, and I mean, it is easy to say why it is correct. The same way the reason the previous one was also correct, because if V is there in the solution, I mean, if V does not go in the solution, then all of its neighbors has to go. Otherwise, who will cover those edges? Okay, so now what is the running time here? Okay, so now in one side, since measure drops by 1 because we are taking V in the solution. On the other side, all of its neighbor goes, but then we know that degree is at least 2. So this leads to a better branching base. And this is the golden ratio. Right. So basically, if you become more, and if you choose to branch on more and more smart decision, that will lead to a better branching base. Like base of the branching will be better. Okay, so now there are many branching and non-branching way of solving vertex cover as well. And the base known so far, the base known vertex cover algorithms base is basically 1.2528 to the k. It's 284 to the k. Okay, so we also know that vertex cover has a factor 2 approximation algorithm in polynomial time. So, and by unique game conjecture, it is known that better than 2 is not possible. I mean, you cannot, in polynomial time, you cannot get 2 minus epsilon time approximation, type approximation where epsilon is greater than 0. Okay, so in other words, factor 2 is in poly time, factor 2 is the essentially the best possible. Okay, so this leads
one
to the
question.
Yes.
Like, what is there any lower bound known on the this FPT? Like, is there any lower bound known?
No.
The size of the
like you can
okay.
if you possible, you can improve more.
Even like polynomial kernels is also
no.
possible.
FPT is like exponential in FPT, right? For polynomial, better than 2 is not possible.
I mean,
under unique game conjecture.
No, I mean, let's say like O star of k square. These kind of things are not possible. Is something like that, no? For vertex cover?
Even that not possible, because if you can get an
oh, I see. Yes.
Right.
Yes.
Yeah. All right. Okay. So this
So
this
for the
leads
base
to
case, are like degree 2 is the right term. Like, so is vertex cover hard even for graphs where degree is 2 or less?
No.
Cycles
For
and
example,
paths.
if the maximum degree is 2, that means it is a graph where it is isolated
Cycles and
vertices,
paths,
paths
yeah.
and cycles, and then it is
Yeah.
polytime solved.
So you can probably like that's how you get an improved bound from 1.6.
Yeah. I mean, you can keep doing more and more until you hit a place where you reach a place where you show that, okay, and now if max this,
Got
like
it.
let's
Yeah,
say C
yeah.
regular or some D regular, it is hard and there you stop. Otherwise,
Sure.
you can improve it like similar way. Like
Sure.
yeah. Yes. Okay. So
So
this leads to the
hi,
question
one
that,
question.
okay, yes.
So till what degree can we say that vertex cover is polynomial time solvable?
Uh,
Three.
I think
3.
3 regular graph for it
Yeah,
is.
yeah, 3.
Okay. So from 4, like it's probably NP hard or we don't know.
Or I think even 3 regular
Even for
graph.
3, it's NP
Three
hard.
regular graph also it
Okay,
is.
I see. Okay.
It's the exact 3 color.
Okay. Okay. I see. Yeah, that's correct.
Okay, all right. So now these two, like in one hand we have an FPT algorithm, and on the other hand we know there is a factor 2 approximation in polytime, and which we cannot improve. This leads to the question: okay, can we do better than factor 2? Let's say 1 plus epsilon, where epsilon is strictly less than 1. But in FPT time, which is not this much, because in this much time we can anyway solve it exactly. So, so the base is better than the base known FPT algorithm, but we allow, like not 2 approximation, but better approximation. Okay, so this, like, can we use best of the both thing? Like here, one side FPT, one side polytime, somewhere something in the middle. So this leads to the FPT approximation kind of questions. Okay, so now we will see FPT approximation for vertex covers. Okay, so now what does it mean by alpha approximation for vertex cover? FPT alpha approximation is that, okay, so suppose let tau G be the minimum size of the vertex cover of G. Okay, so now FPT alpha approximation algorithm for vertex cover is basically, for an instance, it runs in FPT time. Like this FK will be better than the base known FPT. And what is outputs? It outputs a vertex cover of size at most alpha k, or it correctly concludes that minimum vertex cover size is more than k. It outputs one of these two. If such an algorithm exists, then, and which runs in this much time, we call it FPT alpha approximation algorithm for vertex cover. Similarly, since vertex cover is a minimization problem, generally also for minimization problem, FPT alpha approximation is defined similarly, like, or exactly similarly. Okay, so now let's look at, okay, so we will design FPT approximation now, but let's look at the polynomial time approximation, which we will possibly use in order to define, in order to get an FPT approximation. So what is the polytime algorithm? So compute a maximal matching and then take both its endpoints. Okay, and I mean almost everybody know, also in the talk maybe knows. Yeah. Okay, so it is not difficult to show that it gives a factor 2 approximation. So now the question is, can we use it somehow to get FPT approximation? So actually we can. So how do we do? So let's look at before going to 1 plus epsilon, let's look at 1.5 approximation, 3 by 2. Okay, so now let M be a maximum matching, okay, which we compute. So if the size of M is at most k by 2, then you return both its endpoint. And if maximum matching size is more than k by 2, then what you do? You take k by 2, exactly k by 2 matchings and both their endpoints in the solution, and solve the residual, like we have G2, which is the residual instance of the graph, and you solve the problem there exactly with the budget reduced to k by 2. So now you say, then why is it correct? Why should it lead to this 3 by 2 approximation? Okay, so one thing is that the first observation is, when look at G1, when you picked k by 2 matchings, we already know in this graph, since there is k by 2 size matching, vertex cover size is at least k by 2. So if at all there is a overall k size vertex cover, then the k by 2 budget is already eaten up by G1. So you have to find a solution of budget at most k by 2, right? So this is what exactly says, that in the first portion, the vertex cover already is reduced by k by 2. So in the residual instance, you try to solve the problem with remaining budget, which is k minus k by 2, and see whether it says yes or no. Depending on that, you also answer. Okay, so now what is the overall size? So for the first case, you have taken both its k by 2 edge, both the endpoints of k by 2 edges. So here you have already used factor 2 for half of them, and in the remaining you have actually solved it exactly, right? And hence there is no, like, this is exactly you have solved, so there is no additional number here as an approximation. Okay, so this adds up to 3 by 2. Okay, so what is the running time here? So the first part you take polynomial time, and when you basically time is governed by the time when you solve the problem exactly in residual instance, which is like 1.2528 to the power k by 2, and it leads to 1.118 to the power k. So basically you can find 3 by 2 approximation in the time which is better than the base norm, FPT algorithm. Okay, so this is the first glimpse. So you have, in some sense, instead of using the whole matching and taking both endpoints of it, you take it partially so that you can somehow keep the size bound that you want. For now, let's look at 1 plus epsilon approximation. So basically, what does it mean by 1 plus epsilon? Your question asks for k size solution, but you are giving a solution with additionally epsilon k. So what do? You basically you find a maximum matching, and then basically take those additional number that is allowed for the vertex cover for this approximation algorithm. Those many matching edges you take, and take both of its endpoints. And in the residual instance, you again solve. I mean, the remaining is exactly similar. How much you take from the matching, how many edges, their endpoints you already pick for two factor, that you choose depending on what kind of approximation you want. Okay, so this leads to again 1 plus. So this gives 2 epsilon k, and this gives k minus epsilon k, like in the remaining graph. So if you add up, this will give 1 plus epsilon. And of course, this since epsilon is greater than 0, this will be less than 1, and this will lead to a better than exact known vertex cover solution. Okay, so so this way you can modify the FPT algorithm, modify the polynomial time algorithm to get an FPT approximation. So now, for any epsilon, you can see that for any epsilon you can have this time approximation trade-off, where, like, in one hand we have polytime to approximation, on the other hand we have exact algorithm with 1.25 so on to the k, and for every epsilon in between you have an algorithm with better somewhere in between. Okay, so basically this is the time approximation trade-off. This is we mean the, like, if we have this kind of curve, then, like, for the problem we have time approximation trade-off. Okay, so now we will go to the known results, and we'll see.
This is extrapolated, right? Like, in the sense that, I mean, this is not to scale. I.e., when you're close to 2, you actually resort back to your standard, like, to approximate. This is, it's not that you can drive epsilon 0 and you're getting poly in.
No, yes, you are right.
Okay.
Yes.
Okay. But this is not it's not a linear curve.
No, it's not this. I think I should have drawn it correctly. Okay, my bad. So it's not a linear curve. Yes.
Okay. Yeah.
Okay. So now, in general, we won't describe FPT approximation in general. There are lots of techniques and tools, and for upper bounds and lower bounds, and like FPT approximation is growing nowadays, like, and used in many problems. But we will be specific to our paper and to the talk. Okay, so here we focus on the problems which already admits exact FPT algorithms of the form C to the K, and like the polynomial factor, of course. So for those problems which already promises that this kind of algorithm exists, we want to, the next question is, can we now trade the approximation ratio for smaller base in the exponent, such as can we find an algorithm with C prime to the K, where C prime is strictly less than K, but we relax the size or the optimization function that we are trying to optimize. Okay. So now there are many results on this side. So for some of them are as follows. So there is vertex cover problem, 3 hitting set problems, and feedback vertex set problems, even D hitting set problems. And these people have studied time ratio trade-off for these problems over time. Okay, so the thing is that for all these problems, in a sense, the spirit of these problems are kind of D-hitting set kind of problems. Even though feedback vertexes doesn't look like, because feedback vertex can have cycle of any size, but when you see the branching algorithm of it, and then you branch over some bounded many decisions. So like in a sense, it has uh, flavor of de-hitting set when it comes to branching algorithm. Okay, so now Kulik and Satnai in their Fox 2020 paper, they have introduced randomized branching as a tool for FPT approximation, parameterized approximation. So there they have introduced a machinery for analyzing two variable probabilistic recurrences, and by that they have come up with the best known time ratio or time approximation trade-off for vertex cover 3 hitting set. Okay. So after this, the natural question was that how far we can extend this time ratio trade-off to the problems which are not like D-hitting set but beyond that. And does can all the problems satisfy these, like have this time ratio trade-off, or they need to have some kind of property, only then they can. So is there any meta result that kind of turns every branching algorithm to time ratio trade-off, or like we have to, in a sense craft, in a sense you have to solve every problem by hand, looking at this specific property, or we can kind of have a meta result which takes all the problems with it. So this was the question that we were trying to think and resolve. Okay, so then we actually were able to solve some problems which are beyond de-hitting set type problems, and for those we have given time ratio trade-offs. Okay, so in particular we have found a formal language for randomized branching rules, and we came up with meta algorithm that compiles branching algorithms into time ratio time approximation trade-offs. And these problems are beyond the set of problems that I have shown. Like these problems are beyond that. Like there are lots of problems we go which are not like those kind of problems, but like beyond that. We will see, it will come in the next slide. Yeah. Okay, so our frameworks basically gives time approximation trade-off for, let's say, vertex cover above LP, odd cycle transversal, like all these problems we have been able to give time ratio or time approximation trade-offs. Okay, all right. Okay, so we have in this paper we have two kind of contributions. Okay, so one is like first we basically we show that a complex random walks arises from the probabilistic branching algorithm. I'll tell what that is shortly. And for some of the problems, we have used measures which are typically called as above guarantee measures for in parameterized complexity community, which is like not just the solution size, but some smaller parameter, let's say, than that. And in terms of technical contribution, we have tools for analyzing these random walks, and like we have been inspired from Ariel Kulik and Hada Satnai's Fox 2020 paper, and like we have tried to generalize that so that we can solve problems beyond the set type problems. Okay.
So
Okay.
one
So
question.
in this talk, yes.
So in the previous one, did they also consider parameters apart from the solution size, or
not yet? No. For these problems, they have considered solution size as a parameter. So we are considering above guarantee parameterization.
Okay.
Yeah. All right. Okay. So what do we mean by conceptual? Okay. So now when we started thinking on those lines, we were actually reading the Schoening's algorithm for DSAT. Okay, so what is DSAT? We have to find a satisfying assignment for a CNF form, given a CNF formula where every clause is size at most d or has at most d literals, and this algorithm has a random walk viewpoint that kind of made us interested to think those probabilistic branching algorithm as random walks. But the difference is the problems that we are solving and that shown in DSAT algorithm is that this problem is answers only decision answers, yes or no, because you will have to just say that whether it is satisfiable or not. All right. So even if in the middle, if you in your branching or in your decision you make mistakes, it doesn't really matter as long as you end up with a yes state. But for optimization problem, you have to optimize something. Let's say the solution size. So every time you make a mistake, you pay something because you are optimum actually was choosing something, but you are ending up choosing something else. So that much extra you would pay every time you make a mistake. So this overall mistake in your branch will add up to your overall solution size or whatever measure you are considering. So in a sense, in that sense, this is different also. Okay, so now here in our paper, we have to consider two things parallelly. One is progress or the measure, how the measure is changing, as well as how much error we are making during the process. Like at every step, how much error we are making, and overall how much error we are incurring. So we have to kind of be balanced between both of them. Okay, so let's see the vertex cover example and how do we model it in random walk. Okay, so the basic random walk is basically is a one-dimensional random walk where like you have a number line and you have numbers, and these numbers are basically states. And basically random walk is a process that moves between states, right? And it either goes left or stays in the same state, or it goes right. And what is our goal? The goal, we want to analyze the probability that starting at any state you want to reach to the final state within some bounded many states, and what is the probability of reaching to the final state within whatever bound state we want. T is in our. Okay, so now first, before going to random walk view of the branching algorithm, let's convert our branching algorithm to a randomized algorithm. What do? Everything is same, like base cases are same. Instead of branch, so you chose an edge arbitrarily, right? Now, and then you branched on both its endpoint. Instead of doing that, you basically uniformly at random pick one of the endpoint and run and basically move ahead, like take it in the solution and move ahead, right? So okay, so clearly this is correct, of course, because let S be a vertex cover of size at most k. You know that at least one of these two, U or V, is in S, and our algorithm chooses, let's say U is in S, and then our algorithm chooses U with probability at least half. So it correctly, with probability half, it correctly goes to that branch or that residual instance and solves it, and then we recursively saw that the success probability is half to the k. Like at every step you are with probability at least half, you are choosing a correct vertex to be in the solution. Okay, so now how to view this as a random walk? Okay, so let's fix a vertex cover of size at most k. So you have 0 to k states in the walk. So you have those many numbers. So now what does state I means? What state I means? I many vertices are still yet to be recovered or discovered in S. Like we have k minus I many vertices in S, and I many vertices are yet to be discovered. And the walk, clearly the walk starts at k because all in the beginning you have nothing. All the vertices are yet to be discovered, and when you end up at state 0, meaning that you have discovered the solution. Yeah. So now we want to understand with what probability it actually can reach from k to 0. For that, okay. So for that, what does it mean? So suppose I am at state I. So what does it do? Okay. So you know that for any age, what the algorithm. So you know for any age, at least one endpoint is in S, right? So suppose U is in S. Let's say UV is the age. So when with probability half it picks U, then actually I drops to I minus 1, because at ith step the algorithm was yet to recover I many vertices in the solution. Now with probability half it has chosen the correct vertex in the solution, which is U, and so then that's why I have I minus now I have I minus many vertices to be recovered. You have added one more vertex to the solution, or otherwise V can also be in the solution or might not be, and in any case we can safely assume that okay, V is not in the solution, and in that case the work in with probability at most half, the work stays in I. Okay, so this is why I'm saying that we can think of it as an UV both can be in the solution. In that case both of them are moving, work is moving to the one step ahead, as in like I minus 1, but we can very well assume that one is with half probability it is going to I minus 1, and with half probability it stays at I. We don't know what, so in the worst case this happens. Okay, so now now we want to analyze that with what probability the work actually reaches to final state from the initial state in exactly k many steps, right? Okay, so now see that we have k many states and we have to reach in k steps from k to 0. That means we cannot make any mistakes, right? What do we mean by mistake? Which means that at every point of time you have to take left meaning towards the solution. So I am at k, I have to reach to 0, and I'm with half probability I move to the left to go towards 0. Since I have k states and I have exactly k steps to reach to k 0 from k, every time I have to move one step left, and that happens with probability half, and this is why the probability that in k many steps the work reaches to 0 from k is at least half to the power k, because every time it has to take left, and which happens with probability at least half. Okay, and then if we boost it later, then we can say that this actually yields that 2 to the power k branching algorithm. Yeah, like it's same as the branching algorithm. Okay, so now look at okay, fine, what if I allow 2k many steps? Okay, so if I allow 2k many steps and I'm going from k to 0, then I'm actually at most k many times I can actually stay at some some state. I mean in some state I can stay some 5 times, in some other state, but overall I can stay at most k times, and at least k times I have to move towards 0, so that because I have started from k and I have to reach to 0, right? Okay, so these we can think of it as a random coin toss. Like we want to compute the probability that like what is the probability that we reach k, 0 from k within k 2k steps. So this is nothing but we can think of it as like a random coin toss, like unbiased, and probability of getting at least k many heads. So see that this probability turns out to be half. So you see, whenever we allow from k steps to 2k steps, actually it from a 2 to the power minus k, it becomes a constant, right? Okay, good. So then what is in between? Somewhere in between. Okay, I mean I don't allow k steps, I don't even allow 2k steps, but how about 3k by 2 steps? Okay, so similarly, I know that I mean in order to reach from k to 0, I will have to take k many left movements. So remaining is my always that I can stay at some, like overall I can stay or not move to the left. It was like k by 2 here. Okay, so similarly I can get here that the probability of success is basically you compute this way, and we get like 0.91 to the k, 0.9185, and so on to the k, right? Okay, so now we, in order to boost the probability again, success probability, we again do independent trials of this algorithm, and then we get to the running time 1.088 to the k. So do you see? So here also using random walk viewpoint, we saw that we actually take this much time to get in this much time we solve the problem. Whereas by using deterministic algorithm, the like matching way, we have actually been able to get 1.119. So basically here we improved, right?
So one question.
Yeah.
So can we explain that? What does it mean when you allow 2k steps in the algorithm, in the branching algorithm? What exactly is happening in that case? Because I mean, earlier you talked about this k branches and like k steps, and each step with probability half you take one of them. When you have
Right.
2k steps, what exactly the algorithm do?
Yeah.
So in terms of the graph, not in terms of the random work, but in terms of the graph, what does it do?
So when we have two case steps.
Yes. Like when you have case steps, you mentioned that with probability half, you take one of these two branches and continue for case steps. But now you have two case steps. So what
Correct.
exactly
So
you do?
yeah, so what it does that it has to reach from k to 0 in two case steps. So as long as your k steps are, so I call it is success when it moves one step left. Now as long as it is I mean in those two k steps, as long as it is taking k many steps left, then it will be able to reach from k to 0, right? So basically so that's it basically. So with a good probability it can actually do that,
No,
because
I
now it has
understand.
many choices.
I understand the random walk part, but in the graph, like what exactly you do? You choose an edge UV, and then
Yes.
with what probability you choose U and what probability you choose V, and I mean, what is the algorithm in that case? Like when you allow 2k number of steps.
Nothing. You just execute the same algorithm for 2k steps. The exact same algorithm. I mean, it's just you pick an edge, randomly pick U or V, and either pick U, either pick V, just and delete it. And the important point, I guess, is that k is known to you. So you
Yes.
sort of you have a counter. So
Okay.
you pick one vertex, two vertex, three vertex, and once you have picked 2k vertex, you should have an empty like a isolated vertices only.
I see. Okay. Now I understand. Thanks.
So you can only detect when you are at 0. You can't detect whether you are in other states. So you run this exact like simple algorithm for 2k iterations. And if you have an empty graph, no edges, you're done. Otherwise, that's the boosting probability, like 1 over that.
Right.
Yeah.
Yeah, that makes sense. Thanks.
Okay. So now we see that.
So another question is, like as you had in the other case, like you took an advantage of cycles, etc., like degree 2 vertex, etc. In this case, can you do something, or it's complicated? The random work becomes complicated to analyze.
For which case, when degree at least 3 and
so you mentioned from 2 to the power k, you can improve when you have this option that there are degree 2 vertices and those other cases were there. So is it possible to use those properties here as well and get further improvement, or you really want this? I mean, this is kind of you're emulating 2 to the power k algorithm to get this improvement. But if you emulate the better than 2 to the power k algorithm, is it possible to analyze using random walks, or it becomes more complicated?
Yes, it is possible. That will come. If I don't think we have a lot of time, but that will come. So if we use the better kind of branching, that is also possible to, like, there are complications there, but that is also possible to model it in a number. Yes.
Okay, thanks.
Okay.
So you have a much better drift when in instances where many edges have both U and V present in a vertex, optimal vertex cover. Like this half less, I mean, the probability of moving to the left becomes 1 if you pick an edge where both U and V are in like the optimal. So is that something worth? So I mean, in instance like half and half really happens if your instance has the property that for every edge U and V, only one of them is in the. So if I give you an edge UV where both U and V were in S,
Yes.
your optimal vertex curve, you would
Yes.
definitely move to the left. Like so,
Right.
so that's like I guess that's referred to as the drift in these random
As
walks.
in, like that, if you actually look at the random walk where UV both UV both are in the solution, every time you are going for both the cases you are going left. But this random
Yes.
walk is as good as another random walk where you can kind of assume that one is going left and one is staying at the same place. So that's why like I was just saying, yeah, that is better. Like when UV both are in the
Right,
solution.
right. So
Yeah.
I guess my point is that like the worst case for this are instances where like only you. So, but that also gives you some structure. Like, so I'm wondering like
Yes.
if you can do something special for those kind of instances.
Yes, we can. Let's see. Yes, I mean, when lots of neighbors are there, then good, but there are additional problems as well. Like when it comes to approximation, so we will see that. Like if
Okay.
again, yeah, okay. So since
So another
we
small
have half
question
an
is
hour,
like,
let's say. Yeah.
you have around 20-25 minutes.
Oh, okay. Okay.
So another question I have is like, so in this case, parameter is solution size, but let's say with this parameter, is it possible to get the weighted vertex cover some guarantee, like either
In
approximation
this
or?
paper, we haven't we haven't tried like a weighted version of any problem. Like we need to think about that.
Okay.
But we have solved
Thanks.
other kind of problems. Yes.
Okay.
So maybe
So-
possible. Like while we go, maybe I will be able to answer. Let's see.
So in this weighted version,
far we
what's the
did.
FPT parameter?
Like some of the weights, let's say, I don't know.
Okay.
Like weight, yeah, maybe some of the parameters, whatever we want to like. Of course not size, then it will be probably sum of the weights of the solution. I don't know, like weighted version we haven't really considered.
Okay.
All right, so okay, so what is a monotone random walks basically? Okay, so I will skip this slide because so the kind of random walk we saw for vertex cover is basically it is monotone. It either it stays at the same state or it moves towards the final state. It never makes an attempt to go away from the final state. That much I'll say, and then I'll skip this slide. Okay, so and our vertex cover example that you saw, it was indeed monotone. Yeah. Okay. So now let us model the faster algorithm, maybe which where you were saying. Let us try to model that in random walk. Okay. So what was the and see where is the problem or how do we solve it? Okay. So what was the branching? So you pick a vertex, either V is in solution or neighbor. All of its neighborhood is in solution, and we are assuming degree is at least 2. Otherwise, we can solve in polynomial time. Okay. So now, how do we see it? Okay, so of course, basically this is our random walk. And like the states are 1 to k, sorry 0 to k, and with probability p, the walk goes 1 to left, which corresponds to v being in the solution, and with probability 1 minus p, if it jumps towards from state I, it jumps to a state I minus d, where d is basically size of its neighborhood. Right? Okay. So this is basically typically called monotone walks with jumps. Okay. All right. So here, so now basically this leads. Okay. So first of all, this phi we get. So first we and like do the analysis with p and then optimize the value of p, which leads to this phi value. So what our p is basically 1 by 5. Okay, so with probability 1 by 5, it goes to from state I, it goes to state I minus 1, and with probability 1 minus 1 by 5, which is essentially 1 by 5 square, which is helpful. We'll see why. It jumps from state I to I minus d. Okay, so now how does it help? So here we want to solve the problem exactly. There is no approximation so far, right? So now look at the branching tree and consider any successful route to leaf path. Okay. Okay. So now in this path, I mean, since it is a successful path, it will lead to a solution of size at most k. And in this path, it might have taken many decisions. Suppose it has A many times it has moved one step, and B minus time it actually took jumps. Jump mean which is like each jump cost 2, let's say D, which is at least 2. So now we know that A plus 2B has to be at most A, right? And 2, since D is at least 2, I mean we can it can also be 2. So these has to be at most 2, right? Like because for A many times it is taking 1, and for each of the jumps it is taking at least 2, or in particular let's say it is 2. So yeah. So now what is the probability? Okay, so now with 1/5 probability it has moved to one step below, and that has happened A many times. And 1 minus 1/5, with 1 minus 1/5 probability it has taken jump, right? And hence, so and we know in the previous slide we have seen we'll use this 1 minus 1/5 to be this, and then when we put this value we actually get that, okay, for any successful path which actually leads to a at most k size solution, the probability that the algorithm follows this path is actually with probability 5 to the power minus k. Okay, so now again, if we boost this algorithm, we will essentially with constant success probability we'll get like 5 to the k running time, and which will lead to 1.1618 to the which was essentially the branch the base for the better branching algorithm. Okay. So now here doing approximation is slightly harder. Why do I say that? Okay, so now remember that for age it was like very, so for age no, forget age. So I'm saying so when we want a at most k, like we want a solution of size at most k, then we essentially cannot make any mistakes. Whereas when we allow an approximation, then some of the in the branching tree, some of the root to leaves path which was unsuccessful for exact algorithm now becomes successful, because it is not k beyond k, but maybe within the budget what approximation allows me. So some, like all those paths which were success for exact algorithm are still success, but there are many other root to leaves path which actually leads success for approximation algorithms because it is within the approximation budget. But again, the problem is that while doing approximation algorithm, at every step we need to be careful how much a mistake we are doing. What do I mean by that? Let's look at this picture. So suppose V is a vertex and its degree is D, which can be anything, unbounded. Okay, and I am at the place where I want to find an approximation algorithm. So now my optimum, suppose my optimum chooses V, but my algorithm chooses neighborhood of V, which is like basically D. So now then it makes a jump to D, but I don't know, maybe D was n/2. I want an approximation algorithm, let's say k plus 10, let's say, but at now my algorithm has chosen arbitrarily a vertex of degree at least D, right? And that degree can be very high. And in one mistake, I have, instead of choosing V, what optimum was supposed to choose, I have chosen all its neighbors and I screwed. Basically, I have like destroyed the approximation ratio completely, because now in one step, I have gone beyond the approximation budget that was allowed to me. So for approximation, this becomes difficult. So now then how do we modify this branching algorithm, this modified branch, like the 1.618 type branching algorithm, so that we are still locally within the budget? Okay, so we do the following. What do we do? So we still pick a vertex of degree at least 2. Okay, now what is, instead of my branch, the thought process is that, okay, either V goes to solution or all of its neighbors go to solution, but instead of that I am actually picking exactly 2 of its neighbors. That's all. And of course this is also correct, because when all, I mean, at least one of the branch will be correct, because either V is in solution or either V is in solution, then this branch is correct. And if the other branch is correct, when V is not in solution, all its neighbor is solution. So in particular, these two also are in the solution. So we are still happy. So at least one of these branch will be correct. So this algorithm is at least correct, but we are taking slow move. Okay. Yeah. So this way, how locally we kind of control the error is as follows. So look at the table. Here is what our algorithm choice, like columns are the choices that algorithm makes and rows are the choices that optimum picks. Okay. So now you can see that wherever what optimum picks and the algorithm chooses, wherever they matches, like the first box and the last box, their error is 0. There is no error incurred. But wherever there is a change, like wherever it differs what optimum chooses from the what algorithm chooses, there is some error incurred. But it's not too much. I mean, ideally it was supposed to be D, but we don't know what D is, and we don't want to blow up so much. So we have kept, like, per step error, we have kept it to at most 2. Okay. So now whenever we talk about modified branching algorithm, basically we always choose exactly 2 of its neighbor instead of all of its neighbors. Okay. Okay. So now look at the edge. Go back to when we were doing like symmetric branching, where like one of the endpoints of the edge was in the algorithm was speaking. There, basically, even if you make for approximation, even if you make mistakes, you basically make one mistake. As in, you were supposed to be in the solution, but you have picked V, but like you make mistake per operation, you make mistake 1. But here you see the table, right? Here at some point when opt was supposed to be XY and algorithm was choosing, here error was 1. But here when opt was supposed to pick V and algorithm was choosing XY, then error is 2. So now this error becomes weighted, in a sense that when suppose A is the number of time, sorry, my bad. Okay, so suppose A is the number of times it is taking a jump. Now jump means 2, not all. Yeah, so now it is taking jumps and B is basically 1 reduction. Then we are not interested in how many times it is making an error, but the weighted error, right? Initially it was okay because number of error, every time it was 1, so number of error and the additional cost was same. But now sometimes it is 2, sometimes it is 1. So we need to, in a sense, we need a this in order to this random walk looks complicated and it doesn't remain an one dimensional. This analysis doesn't remain one dimensional anymore. So we need to define like more, I mean, refine state space, and like we see how to solve these recurrences. Okay. So now this is nothing. Okay. So now you can kind of realize that there are 2 things happening side by side. One side it is the parameter, how parameter is reducing, and on the other hand we have to control the additive error, which can be like it's not constant as such. I mean, it's not one constant, but it can be 1, 2 depending on what problem we are solving and what are the branching, how it is reducing. Yeah. So the walk now becomes a 2-dimensional walk. Okay. So now the state space lives in Z2, and where every like BK, basically B stands for how much, for this instance, how much additional error the algorithm is allowed to make in this instance, and K is the remaining parameter budget. Okay. So now what we do, we actually do not look at 2-dimensional random walk at all, but we study an equivalent probabilistic recurrence that started from Ariel Kulig and Hadas Sajnai, their Fox paper. Like they have done some similar kind of things, but we needed to generalize it to in order to capture the problems that we consider. But the starting point was that. Yeah. Okay. So so let Pk be the worst case success probability, where K was the remaining parameter and B is the additive error budget that is allowed. Okay, so now the recurrence looks like this. So where this recurrence comes from? Okay, so again we are in the vertex cover problem, and either V or XY, and that's the branching that we have in mind. Okay, so now the first row corresponds to when V is in optimum. Okay, so now when V is in optimum, there are two cases. Either algorithm picks V, I mean, imagine the table. Either algorithm picks V or algorithm picks XY. When algorithm actually picks V, the measure drops because optimum size, V was in optimum and algorithm correctly chose, so the measure drops. But when algorithm chooses XY, then V was in optimum and algorithm didn't pick V, so the measure doesn't drop. But in this instance, you are allowed to have an error B, but you have made two errors now. That is, you have picked XY, where that was a mistake. So now you are additionally, I mean, yeah, in the remaining instance, you are allowed to make B minus 2 many mistakes. So this is, and similarly, when V is not in opt, these are the two situations which corresponds to those two table entries of the table. Yeah. So now this recurrence, so this is the probabilistic recurrence. So instead of looking into a two-dimensional random walk, basically we want to solve this probabilistic recurrence. Okay, so so this kind of probabilistic recurrence, this kind of machinery was introduced by Ariel Kulik and Hadass Satnai in their Fox paper, and where they have introduced randomized branching for, as a tool for the parameters complexity. So we have generalized this machinery. In particular, we have two more things, like two more relaxations. One is, okay, our parameter, instead of just every time reducing, our parameter may very well increase. Okay, but in a, overall in a bounded way. But locally, our parameter may increase, and the branching probabilities, which is like what I am saying here, 1 by 5, and this is 1 minus 1 by 5. It might not be that. What I mean by this, so the branching probabilities may add up to something less than 1, in which case for the remaining, we add a kill state. I mean, for vertex cover examples, you will not encounter this, but there is another problem that we have solved in the paper. There we needed to have this kill state, which basically means that when your walk goes to the state, it cannot recover. Okay, so okay, so let's go to the general model. So what it is? Okay, so we introduced two matrices. One corresponds to the error incurred, like the error from a branching from. Okay, so for our branching algorithm, we have set of pre-processing rules and branching rules. For every branching rule, we have such two matrices. One captures the drop in the measure. It can like increase, decrease, and B is the additive error that is incurred from a parent call to a child call, like two consecutive calls in the branching tree. So these are the two matrices. Okay, so let us see this in this example. So again, okay, this is a typo. The neighborhood might not be exactly this, but we consider two of its neighbors. Okay, so is the same branching V. Either you choose V in one hand or you choose two of its neighbors. Okay, so now how do we how these B matrices are, B and T matrices are defined? So look at so rows. The first row of both the matrices correspond to when V is in optimum, and the second rows of these two matrices correspond to when the other decision is taken, as in when V is not in optimum, when U1, U2 is in optimum. Now, in terms of columns are basically the decisions taken by the algorithm. So if you visualize the table, basically whatever the numbers are populated in the table, one is for B and one is for T. Okay. Okay. So recall that for monotone case, like what we saw when all the entries of the T matrix were non-negative, then it basically is the monotone case. But here we will see that it can be negative as well. So if I have time, I'll slightly talk about vertex cover above LP, where we will actually see not the whole solution, but we will see how measure can actually increase locally. Okay, so what is the problem? Again, the vertex cover problem, only difference is the parameter is different. So what is the parameter? Okay, so for a given graph G, let lambda denote the optimum value of LP relaxation. So you know the LP relaxation of vertex cover, right? So then let lambda G be the optimum value for that LP relaxation and ought to be the size of the optimum solution, like size of the optimum vertex cover. So then our mu is basically twice of opt minus lambda G. Well, you know that this lambda G is a lower bound on the optimum of minimum vertex cover size, right? So that's why this is an above guarantee parameterization, and which is more interesting because it is a smaller parameter, because I mean opt minus lambda G is less than equal to size of opt, right? Okay. So we consider
what is the motivation? So what is the motivation behind this thing? Like why 2 times this parameter?
yeah, that is, this 2 is nothing. This is just for practical purposes. We wanted to keep everything integer, like somewhere half type of things were coming. In order to keep everything integer, we just multiplied by 2. And there is no, like conceptually, there is no reason for it. Like we could have very well not do it and handle it in a different way. Yeah. Okay. So let us see. Okay. So first of all, vertex cover above LP is a like interesting problem, and it actually captures many problems like vertex cover above matching, and then almost two set or OCT or cycle transversal, and like many problems it captures. So it is interesting to study that in this model. Okay. So now before going to
So
the
one question, like
branching,
it captures them with what parameter? The previous problems, like all.
like
So this is
okay,
what
I think
parameter?
I'll have to check that. So for vertex cover above matching, it will be the parameter will be say vertex so opt minus maximum matching size, for
Okay,
example.
so there are
Like
different
above
parameters you define.
right, and there will be a relation between this and this. Like we can, I think, show a reduction. Not reduction. I think vertex cover above LP, like LP is less than equal to maximum matching, like size of maximum matching of G. LP of the LP relaxation, like the lambda of G, which I was saying, this is less than equal to maximum matching of G. So this is even smaller parameter. No, yes, no, or larger term. And I think maximum matching of G is greater equal to lambda of G. But then I think, yeah, I mean, if we need to think, if we solve these, I mean, we can solve all these problems in what way? Like, I'll need to think.
So for like for example, SAT, etc., there the parameter is what? Like because there is no LP, like vertex cover LP there. So
Right. Like,
anyway, fine. Like
yeah, I'll need to think a little bit. Yeah, okay. So maybe we can quickly see how for this problem how the parameter can still increase.
I guess
Okay.
you have around 5 minutes just to
Yeah, okay. So okay, so there are the standard assumption that we can make, like we can assume that we have done some pre-processing rules on the instance given. These are standard pre-processing rules given in the like parameters complexity blue book. At least there I know there are many places probably it will be given that the LPs all have we can pre-process in such a way that the LP has unique all have optimum solution, and we can also we assume that the graph has degree at least 3. Otherwise we could have done something. We do the pre-process to the graph, pre-processing to the graph as long as we can do, and the when we cannot do, we have these assumptions. Okay. So now our branching rule is same, like either V is in solution or U1 or U2 is in solution. Okay. So now let's see how our we will see that how a wrong move, like a wrong decision, can increase the measure. So suppose we are in the situation that V is in opt, okay, and we know that U1, U2 is not in opt, okay. So now suppose our algorithm has chosen U1, U2 in the solution, so it has definitely made an error. But let's see how. Okay, so since V is in opt and algorithm did not choose V, so opt remains same in the remaining. But since it has chosen U1, U2 in the solution, and we have assumed that all half is an unique optimum, LP optimum. So when we choose this in the remaining graph, basically for half is reduced for U1 and half is reduced for U2. So overall one has been reduced. So the remaining budget for LP is basically one less than the old one. So then what is the like updated measure? Basically twice of updated opt minus updated this, and then if you replace that, you actually see the measure increases. So what does it mean? That if you see the BNT matrix, where for every branching rule we have one such BNT matrices, then we see that like it consists of positive, negative, all sorts of values. So if you look at consider Ariel, Kulik and Satnai's Fox paper, their model, they only considered when the matrices are a T matrix consists of non-negative values. But like we needed, for some problems we needed, for example, in particular this problem, we needed that T possibly consider all sorts of integers or all sorts of values. So and that we could achieve by generalizing the model. Okay. So so we can visualize this this as a two-dimensional random walk, but we actually do not go into that. Instead, we try having for every branching rule and having a BT matrix for each of them, we try to solve this probabilistic recurrence, yeah, and which eventually solves the problem. And for that, we use those technical tool that we kind of generalize from their model. Yes, which we will not talk now. So in other words, okay, so let us in kind of summarize that what we have. So we have set of minimization problems, and we have for those we can assume that first of all we can assume that all these problems we call these oracle subset problems. We can assume that all these problems have exact FPT algorithm to solve that problem that we already have. Now we have some branching rules, some pre-processing rules, branching rules of constantly many branching rules. Like it cannot be unbounded. And we have certain measure that tracks the progress, and we have B and T matrices. Having all those, so basically, and we also have an oracle that can answer many things. Like you can kind of assume that okay, it is a metroid oracle which says that whether the set is independent or this kind of oracle. In fact, we also in our model we solve the what problem do we solve? Metroid rank vertex cover, Metroid de-hitting set. All these problems also like we solve in our model. Yeah. Okay. So yeah, so basically for these for all these problems, we give a time ratio trade-off, time approximation trade-off, and like which is beyond like whatever was known before. And yes, so this is these are the problems problems for which we could and many of these problems as for them, like we have considered like above guarantee parameters, as you have seen, like for above LP, like vertex cover above LP or something above something. And yeah, so these are the problems we were able to solve in this paper. And
so one question, you mentioned that non-FPT results are shown in blue and your results are in green, but I don't see them. Like
sorry,
so in the table you mentioned that non-FPT results are shown in blue while our results appear in green.
No, that's my bad. These are the known things, and we are showing that okay. So for some constants like 1.25 or 1.5 and so on, for these are the times that we get. For and mu is the appropriate measure chosen for the problem, like mu, k, whenever, whatever. Yeah. So yeah, and then okay, so conclusion is that okay, so the thing that still remains open is that whether can we show time approximation trade-off for, like, say, planar vertex cover and directed feedback vertexes. Maybe weighted version also we could probably think of. We didn't think. I don't know. So that also we can try, and also, like, we can go beyond. I mean, we can extend the Kulig's framework even farther, so that we can capture even richer random walks coming out from the probabilistic branching algorithms for those problems. And yeah, another question is, can we obtain a deterministic? Can we de-randomize these algorithms? Yeah. So these are the.
So are there any questions
Any
for the speaker?
question?
So I did not understand the part where you said that. So for exact solution, this jump will not create a problem, but for approximate solutions, the jumps will create a problem because we can lose a factor of like d there, where d is unbounded.
Yes. So
So can
let's
you explain that
go.
again once again?
Okay. So, oh, right. So, see, suppose we are choosing, suppose we want to model this as a random. Okay. So, in one hand, we choose V in the solution, on the other hand, we do not choose V, hence all its neighbors. Suppose this
Right.
was these are the two branches, right?
Right.
So now its random walk will be basically, okay, with probability p, we move from I to I minus 1, and, like, for appropriately chosen p which minimizes the time. So forget that, maybe, like, there is some p for, yeah, and for with probability 1 minus p, you move from I, jump from I to I minus d, right?
Yeah.
So now, and d is at least 2, so you make a jump of at least I minus 2. Yeah.
Right.
So now, so what is the issue? So suppose you are given with an instance where every vertex, the degree of every vertex is very high. Okay.
Right.
Okay. So now, and you want to find an approximation algorithm for, let's say, k plus some 10 to the power 10, which is also a constant. Let's say k plus 100 for that matter. Okay. And
Okay.
n is huge. Okay. So now, if so now whatever vertex you choose and try to branch on, when you take a jump, you will already go. So what is it when it comes to approximation? This is the exact thing I'm saying. But when it comes to approximation, suppose V was supposed to be in the solution, okay, in the optimum solution. But what
Right.
algorithm does? Algorithm is allowed to make a mistake because we are not solving it exactly, right? So some mistake is allowed, but locally algorithm doesn't know that while taking this decision, I am whether I am making a lot of mistake or bounded mistake. So
That's correct.
if it blindly chooses a vertex whose, let's say, degree is, say, n by 2, and n is really huge, then it is actually choosing all the n by 2 vertices in the solution. But maybe your approximation algorithm, like that you want to design, it allows you to let's say k plus some 100, but it already, in one step error, you already blew up
Okay.
an error
Okay.
to, like, yeah, n by 2, but maybe n is like 10 to the power 10, and then you are screwed in one step. So
Okay.
that's
But
what I
in like
mean by,
when trying to find like exact solutions, we don't face this problem.
no,
I mean, it can
you
so
have to,
happen.
for trying to find an exact solution, you have to take all the right every
Okay.
time you
All
have
the
to take the right
I see.
decision. So you are not allowed to choose NV, or in other words, if you choose NV, it will lead to a no instance. So
Okay.
the
I see.
only
Understood.
way you can go to, yeah.
Understood. Okay. Thanks.
Any more question?
If there are no further questions, then I thank the speaker on the behalf of the audience. So, yeah, thank you, Madhumita, for a nice
Thank you.
informative talk.
Thank you. Thank you very much.
Yeah, thank you.
Okay. Okay. Thank you. Okay, bye then.